Hi, this is Sindoja. I'm from Hyderabad. Yeah, presently I'm doing my summer semester. So, first question asking me your presentation is what is fuzzy matching and how it differs from exact matching? Here, if I want to say it like, if I consider exact matching, it like requires every character, every space, punctuation, everything should be matched exactly. Like in fuzzy matching, like it just takes some of the text and we can search with that so that it gets, but not like exact matching. So here definition is like it seeks a perfect match between uh, like data entries required exact alignment of characters, spaces and all. When comes to precision, like it is high, only exact matches are written. And like we can use cases are like where we can use this like database keys, passwords, ID numbers, that where accuracy is crucial, we use that. And limitation is like it fails if there are any differences such as typos, and fuzzy matching is like it finds appropriate matches by identifying similarities despite small differences errors. And flexibility is like here can match entries with minor errors or variations. And use cases are like it can be used in like data cleaning, search engines and text analysis. Yeah, that is what if I want to mention differences exactly, here we can like precision versus flexibility we can consider. Exact is like exact matching is like requires exact correspondence, high precision, and fuzzy is like allows for partial matches, more flexibility. And when comes to error handling, exact is like does not tolerate disappearances, but fuzzy is like handle typos and variations. And when comes to performance, exact is like faster and less computationally intensive, and fuzzy is like more computationally demanding. So when it comes to examples, exact matching is nothing but like if I want to consider if suppose my name is Sindhu, so it finds only if I type SINDHU. If I type the same thing, then only it comes. But in fuzzy matching, if I type like SID also, yeah, it takes similarity recognition and it catches the word. So yeah, that is like fuzzy matching is useful for imperfect data. Like exact matching is used for like scenarios requiring strict precision. Yeah, that is what. And when comes to my second question, it is like key similarities and differences between Edelman-Wunsch and Smith-Waterman algorithms. So similarities like both can use dynamic programming, and differences is like we have some similar like kinds of differences like matrix, traceback, and application. I will explain them one by one. So here mm are both used for sequence alignment of binoinformatics. When it comes to similarities, dynamic programming, if I want to explain, both use dynamic programming to find optimal alignment between two sequences. And when it comes to, if I want to explain about scoring, they incorporate matching, rewards, mismatch penalties, and gap penalties in a scoring matrix. And if I want to explain about alignment types, both can handle DNA, RNA, such things with adjustable scoring schemes. And if I want to explain the differences, and that is first one is purpose. That is Needleman Wunsch, that is like designed for global alignment, aligning entire sequences. Waterman is like designed for local alignment, as I said before, finding the best matching sequences. And matrix, when it comes to matrix initialization, in this Needleman is like initialize the first row and column with the gap penalties. When it comes to Smith-Waterman, it initializes the first row and column with zeros. And if I want to explain about traceback, Needleman is like traceback from the bottom right to the top left cell for full sequence alignment. When it comes to Smith, it from trace back from the highest scoring cell to the cell with zero for the local alignment. So when it comes to application, Needleman is like used for aligning similar length sequences like entire genes or proteins. Smith is like identify similar subsequences with larger sequence. Yeah, summary is like Needleman is for global alignment entire sequence, and Smith is like local alignment subsequence. Yeah, this is what. And the next one is like how does BLAST utilizes heuristics to spend the search for sequence similarities. This is like BLAST is like nothing but basic local alignment search tool uses heuristics to spend like to speed up the search of sequence similarities, like by breaking the query sequence into smaller words and looking for the exact matches of these words in the database, so that significantly it reduces the search space. So I can explain how it works. Like in words matching, BLAST, as I told you, like BLAST divides the sequence into short pixel length subsequence called words. In hash table, it uses the hash table for a quickly find exact matches of the words in the database sequence. And word extension, once a match is found, the BLAST extends the match in both directions to find high scoring segment pairs. And also in HSP filtering, BLAST filters out like low scoring alignments, focusing on high scoring ones to further refine the results. And by using these heuristics, BLAST reduces the number of sequences and also like regions that need detailed comparison, making it much faster than what we say traditional programming methods, dynamic programming methods. That's what my blast one. And the third question asked is describe the steps involved in the level order travels algorithm by providing examples using binary trees of your choice. So this is like level order traversal is also known as Burt first that is BFS. So it visits each level of the binary tree one by one from top to bottom, from left to right. So here is like algorithm I will explain. So steps involved in the level order traversal are initialize a queue, use a queue to keep the track of each node to visit by enqueuing the root node. So process nodes like level by level while the queue is not empty. Till then it continues to work, and dequeue a node from the front of the queue, like, and visit the node, then enqueue the its left to right children. So I will show you with the example. Here I took the example is like 1 and 2, 3 are children of 1 and 4, 5 are children of 2 and 6 is child of 3. So here first I queue 1, then I DQ1, so it visits 1, and the children of 1 are 2 and 3. So from left to right, I have written. So in queue, it is like now as 1 is visited, in queue there will be 2, 3. If I come to next, next one is like 2. So here I DQ2 and visit 2. So in NQ there will be children of 2. So that are 4 and 5. So 4 comma 5. So in Q, there will be as 2 is visited. So in Q there will be 3, 4 and 5. So this will be in 3, 4, 5. So next we go to 3. So here we DQ 3, visit 3, and NQ are like what are the children of 3, that is 6. So it is 6. So here in Q now we will be having 2 is visited, 3 is visited. So we will be having 4, 5 and 6. So now we will visit 4. Here we can see that 4 has no children. So here we DQ4, visit 4, and NQ is none because 4 has no children. So NQ there will be 5 and 6. Again same, we will go to 5, visit 5, and NQ here also none because 5 has no children to write. So here there will be again only 6 in Q. So now I will DQ6, visit 6, NQ none because no children of 6, and Q is like, here Q is empty. So we should do until this is empty. So now it is empty. So now if it So the order it is visited is like 1, 2, 3, 4, 5, and 6. Yeah, this is what my level order traversal. So the 3.2 question is analyze the time complexity and space complexity of the level order traversal algorithm in the worst case. And they also asked to provide example of height 4. So that is what here asked. So here time complexity analysis is like the time complexity of level order traversal in the worst case is big O of n, where n is the number of nodes in the binary tree. This is because like node is n-queued and d-queued exactly once. That's what. And space-time complexity is like the space complexity is big O of W, where W is the maximum width of the binary tree. In the worst case, the times are space complexity, space complexity becomes big O of n, where if the tree is a complete binary tree and the maximum number of node and the widest level should be off of the total number of nodes. So here if I want to take the tree with a height of 4, say this is, so 1 has children 2 and 3, 2 has 4, 5, 3 has 6, 7, 4, 8, 9, 5, 10, 11, 6 has 12 and 13, and 7 has children 14 and 15. So here is also same where I have done on the top level order traversal. Here also we do the same. Here first we queue the 1, then we dequeue 1, visit 1. So we have already visited 1. We will write, we enqueue the children of 1 that are 2 and 3. So next, again in the same way as I have done on the top, next we will DQ2, visit 2, but we NQ, it is 3, 4, 5. And next we go to 3, we like visit and we write children are 6, 7. So now in NQ we have 4, 5, 6, 7. And again like same, 4, 8, 9. So in the same way at last, the order will be like 1, 2, 3, 4, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 15. Sorry. Yeah, this will be my order. Mm, yeah, that will be my, nodes are visited in that order. So die complexity is big O of n because every node is processed once, that is n-queued and d-queued. So space complexity in the worst case is also Q will be hold the largest number of nodes at any single level, which for a complete binary tree, there is at last the last level. So here the size is 4. So for a complexity of binary tree 4, the last level has like n by 8. So it implies big O of n, the space complexity when n is large. Yeah, this is my explanation. Thank you.